Hey, what's up, anime enthusiasts? We're going to talk about forces and free body diagrams today. So, these two ideas are kind of the cornerstone for the next couple of units. We're going to use them liberally. And I don't mean politically left, I mean, we're going to use the heck out of them. The start of almost every single force problem should start with a free body diagram. And forces are one of the most fundamental things in physics. They're how we'll look at energy, they're how we'll look at spinning stuff, they're how we're going to look at momentum. They basically are what drive the universe. So it's important that we understand them. So today what we're going to do is we're going to basically just I knew it. It never works. It never happens the way it's supposed to. Beautiful. We're going to talk about what is a force qualitatively. We're not going to calculate anything today because calculating is a little harder than we want to do on the first day. We're going to talk about several common forces. I have 4 of them, and these 4 forces cover almost every force we're going to talk about in this class. There's a few notable exceptions, but not many. And we're going to learn how to make a free body diagram. Disclaimer, I learned free body diagrams as force diagrams. So if I happen to say force diagram and I don't make a distinction, they're the same thing. I just think that free body diagram is more aligned with the AP test, whereas force diagrams are just whatever my professor decided to call them. So, you know what I mean. A half dozen of these, 6 of those, whatever. Same idea. So, let's go talk about it. Let's start with some vocabulary. Let me define a few things for you. Just so we can start to get the feel for forces and how to operate with them and what they're good for. So a force is really just any push or pull. It's that easy, right? Anytime something's pushing on something or pulling on something or generally shoving something, making it move differently than it did before, there is a force involved there. Forces, thank goodness, are vectors, meaning they're going to move. They're going to have a direction and they're going to have a length. So the direction of pushing something is important, right? If you want a car to go forward, you can't just, willy-nilly push that thing any direction you want. You can't get on the side of the car and push sideways. It's not going to go forward if you push sideways. You have to push forward. So obviously, direction matters, and so does how hard the push or pull is, or the magnitude, the strength of the force. Okay, let's go ahead and just get this out of the way. Almost everybody knows the equation for force just because it's almost like a meme, right? It's one of those equations that just everyone knows. Just like E equals mc squared, just because. You probably know the equation for force already. As an aside, this is not the correct equation. There's actually a gamma in there that no one talks about, but that's for another day. So the equation for force is F equals ma, or mass times acceleration. The only reason I bring this up today, we're going to really hammer this in another lesson and see how to calculate with it. We're not even going to need an equation today. We'll bring up a couple, but it's for later. The reason I bring this up is because these will help us figure out what the units of force are. And whenever I define something, I like to give you the units for it as well. So force is mass times acceleration. So the units for force are equal to the units of mass, and we measure mass in kilograms, times the units of acceleration. And the units of acceleration are meters over seconds squared, or meters per second, So the unit of force is a kilogram meter multiplication dot per second squared. And you're going to say, what the heck does that mean? This is one of the first units that we get where it's just so complicated. And if you sit and try and dissect what this is trying to tell you, you're going to make your brain hurt and then you're going to hate physics. So this is the unit of force. But because this is so ugly and cumbersome to say, kilogram meter per second squared, right? We have a relabeling of this. There is another unit for force that everyone uses, but it's made of these things. So when we say this other unit, really what we're saying is a kilogram meter per second squared, but that's a mouthful. So the unit that we replace that with for simplification reasons is called the Newton, and it is a capital N. So the units for force are newtons. Capital N is the symbol. 1 Newton is a kilogram meter per second squared. Okay. There you go. All right. Let's talk about free body diagrams. I'm going to give you some rules, but let me kind of describe what they are to you. A free body diagram, sometimes called a force diagram, is a diagram that helps us visualize the direction and the magnitude of forces. Basically, it's a picture of what forces are pushing on stuff and what direction they're going and how hard they're pushing. That's all they are. So one of the reasons I really like physics is because it gives me an excuse to like draw a whole bunch. Yeah. And then we can like make it a JoJo character. Look at that jawline. Put a big old nose on him. Dude, what an ugly nose. But force diagrams are basically drawings that help us visualize the direction of stuff. So we're going to be drawing a lot of pictures. I've pre-drawn some of my pictures, but we're going to draw the force diagrams or the free body diagrams today. The last thing we want to talk about, just because it comes up and it's one of those things that you might get different definitions for different sciences. So let's talk about how we want to think about mass. So mass, the way I think about it, is mass is a measure of an object's resistance to being accelerated. Okay? Think about it. It's like your little brother or sister, whichever one you feel like bullying in this scenario, right? They're sitting on the couch. What's the couch look like? Something like that, right? Anyway, they're sitting on the couch and their feet don't even touch the ground, right? There's your little brother or sister. And then you come over and then you sit on them because that's what big brothers and sisters are for. You sit on them and they go, "Get off me. You're," and then they use a very phobic word, "fat." They call you fat because you're big and they push on you and it's hard for them to move you. What they should say, what's a little more scientifically accurate, is they should call you massive instead. Because you have so much mass and it's hard for them to accelerate you or get your velocity to change. It's hard for them to get you to move. So mass, in chemistry, they like to say it's like how much stuff there is. Right? And then they kind of put like quotes around stuff, right? It's how many atoms there are. But really, it's not a number of atoms. That would be like a mole, right? And it's not like how much space you take up, because there's things like lead that take up very little space but weigh a lot. So when we say things have a lot of mass, what we mean is it's hard for us to make them move. Okay? So mass is the amount that the stuff you're made of resists moving. And that's how we're going to think about mass, right? It's a resistance to being accelerated. It's hard for people to make stuff move, okay? So, with that in mind, let's go talk about how to draw a free body diagram. So, for drawing a free body diagram, there are a couple of important things we're going to do. We have to define an object. In most of the examples, it says something like there is a mass. Okay, mass being synonymous with box, not box. It's just something that, you know, is made of stuff. It doesn't really matter what it is, right? It's a mass. So what we're going to want to do first is we're going to want to condense the object down to a point. Really, when you're like moving stuff around, you've got your box here. But like you could push over here, you could push over here, you could push up there, you could push on the side over there. You could push kind of like diagonally from the back there. You could push on it from the back. You could pull it, right? You could do all kinds of stuff to this box. We're not going to worry about where you're pushing on the box. We're going to take this box and we're going to turn it into a black hole. And now it's that. And now everything is just doing that, right? This helps us avoid any like, well, what happens if I push on the corner instead of right in the middle? We're not going to trip about that right now. We will trip about that in a later lesson when we talk about things called torques. Then it's important. But for right now, don't worry. Just take that thing, turn it into a singularity, and put a dot. That's our mass. Okay. Then we're going to draw our forces on it, and we're going to draw them as vectors. When we say vector, what we mean is a ray, meaning an arrow on one end and then like a not arrow at the other end, a finite stopping point. This thing is a vector. So we're going to put the tail of the vector on the singularity, and then that's it. That's our force. We probably want to label it force, but, you know, or whatever force is being applied. Okay. The vector should point in the direction the force is pushing or pulling. So if this is a butt on your little brother, maybe that's a bad way to represent it. We should, ooh, why is it erasing? That's weird. What in tarnation? Okay. We should probably take the butt force and put it down, because butts push down on stuff, right? We're also going to, only forces acting on the object should appear on the diagram. One mistake that students often make is they'll say, but my butt is pushing on my brother, so I need to put that force on there. No. We only care that your brother is pushing on your butt. And I'll show you some examples of what we mean in the examples when we look at like real stuff instead of just these vague imaginings. The last one is that free body diagrams should only have forces on them. Okay? No velocities, no accelerations, no masses, no displacements, no anything else that you want to put on there. It's a free body diagram or a force diagram, so it should only have forces on there. No accelerations and velocity. All right. That's what you need to know about force diagrams. Let's take a quick look at some forces, just so you kind of know what we're talking about when I use certain words, and then we'll go draw some pretty force diagrams. Okay, here are the 4 most common forces that you will see in this class. So I want to tell you about some of the nuance about them, just so we know what we're looking at first, and then we'll go draw. All right, let's talk about the normal force. This is sometimes also called a contact force. This is the force that happens because one solid object is pressing on another solid object. When we say the word normal, we don't mean normal like people who don't pretend to be Pokemon at school in front of other people and run around the playground shouting Pikachu at the top of their lungs, or people who don't like smooth peanut butter. You know what I mean? Smooth peanut butter. If you like those little chunks in there, you're a weirdo. Now that you're nice and offended. When we say normal in this case is actually a math word. It's the same thing as perpendicular. Perpendicular. Okay. There's a third word for perpendicular that you'll learn someday. It's also orthogonal. That's probably not spelled right, but perpendicular, orthogonal, and normal all mean the same thing. When we use the word normal, this kind of has a certain connotation to it. If you have a piece of paper, so let's say here's your desk, right? And you've got a piece of paper sitting on your desk. Normal means perpendicular to a flat surface. So the perpendicular would be like straight off of the piece of paper, right? That's what the word normal means. It means perpendicular to a flat surface. So we're not saying this is like an average or like a common force. We're saying it's a perpendicular force. All right. Tension is not the thing that you feel when you're at parties and you don't know anyone there and you're like, oh good, they have a dog so I can pet this and pretend to fit in. Tension is what we are talking about when you have like a long malleable thing that you pull tight. This is for like strings, chains, any like wiggly thing, wet pasta. You feel me? Anything that's kind of like this and that you can pull tight into a thing, that's what tension is for. One important bit of nuance about tension is that the force, force is a C. Force is always in the direction of the, I'm going to put string here, but you get what I mean, right? It doesn't have to be a string. Could be a chain, could be some pasta. So if my string is going this way at a little angle, then my force is parallel to that string. You can't have a string this direction that pulls something that direction, right? Strings don't pull up but push right? When you pull up, they pull up. So they're always going to be parallel to the physical object that is applying that force. All right, you know what friction is. Friction is that thing that makes your knees hurt when you fall off bicycles, and that gives you rug burn, and that makes it hard for you to like slide around. Friction is just two objects rubbing together, right? So we could call it a rubbing force. Let's talk about friction. If you have a flat surface and you have something on that flat surface, if I push this thing that direction, friction is trying to resist that motion. It doesn't like that you're pushing on this. So it slows things down, right? It doesn't, if you like roll or if you slide something across a floor, it doesn't speed up until it hits a wall, right? If you slide something, it slows down and gradually stops. That's because friction is always going to push in the opposite direction of motion. It's also always going to be parallel to whatever surface you're rubbing on, right? So if your surface is like this and you're sliding that way, friction is going to push that way parallel to the surface you're on. So normal forces are perpendicular, frictions are parallel. Technically, they're both contact forces because normal forces are solid things pushing on each other. Friction is also solid things rubbing on each other. So some people group normal force and friction together as a single contact force, but it depends on who's teaching it, right? Because so often we care about the vector components of a force. We care about the direction a lot. Most of the time, we will break this contact force up into the perpendicular piece and the parallel piece because it just makes problems easier. So usually we'll leave the normal force and the friction separate. Okay. The last force that is super special and in almost every single problem is weight. Weight occurs because of gravity. Okay. So when we say, what's the weight of an object? What we're really asking is how hard is gravity pulling on that object? So weight is equal to the gravity force. You shouldn't have weight and gravity on the same object because they're the same thing. It's redundant, right? So when we say weight, we mean the force applied by gravity. And let me go ahead and just give you the equation for it. We're not going to use it to calculate anything today, but I might as well because it's so easy. So the equation for weight is equal to the mass of the object, or like how much it resists motion because of all the stuff that's there, times little g. So this is a mass times an acceleration. So mass times acceleration is force. The weight force is the mass of the object times a specific acceleration. So weight is also the same thing as force of gravity. So you might see it as weight, you might see it as force gravity. It kind of depends on the context. The equation for both those things is the mass of the object that gravity is pulling on times little g. And little g, just one more time for those in the back, is 10 meters per second squared down or towards the center of the earth. Okay, so there's the four forces that we're going to see the most often. Let's go use those and draw some pretty pictures. Okay, first example. Easiest example I could come up with. We have a box. Oh, it's locked. How dare I? Sitting at rest. So it's not even moving. It's just sitting there on a table. We want to draw the free body diagram for the box. Okay. So step one is take the box and turn it into a singularity or a point. Okay. There's my box. I don't really need to worry about, well, is it spread out over the whole bottom, or is it just in one spot, or is it on each individual? Don't worry about it. It's a dot. So we turn our box into a dot. Now we need to ask ourselves what forces are acting on this box. Okay. Well, this box is on a planet, and planets have gravity, and gravity pulls stuff towards the floor. So the first thing we're going to do is we're going to put the force of gravity on it, put that down, and we're going to label that arrow or this vector or this force vector with some label to tell us what this is representing. I'm going to put W for weight. So this box has weight pulling it straight down. Force of gravity is pulling down on our box. Okay. Why doesn't it fall then? If there's gravity, let's see, why do things fall? If you jump out of a plane, you fall, right? If you roll off your bed, you fall. If you throw a ball into the air, it falls. Why is this box currently not falling? Well, it's because this table is in the way. There's a solid object in the way that's pushing back on it so that it can't move. There's something resisting gravity, like the ground or a table, right? So because gravity is totally canceled out, it's canceling the gravity trying to make this thing fall, that force must be in the opposite direction. So there is a force pushing straight up on this box, and it's equal. So I'm going to put the little like geometry symbol for equal, the little marker. Because the thing canceling it out is this table pushing up on it, that's a solid object pushing perpendicular to its surface on another solid object. This is a normal force. So this would be our free body diagram. One important thing that you kind of want to note about forces is you can only have a force if there's something touching the object with, for right now, one exception. The only contact-free force is gravity. Only gravity can apply a force without touching. Okay. If you want to have a normal force, you have to have a solid object touching another solid object. If you want to have tension, you have to have a rope tied to something. If it's not tied to it, you'll pull on the rope and then it just won't be attached and it'll fall off. If you want friction, this is two objects rubbing, right? It takes two to tango. You can't have friction without a second thing to friction on. The only thing that can apply a force without touching something is gravity. Mr. Barton, what about magnets? Okay, that's one of those exceptions, but we're not going to talk about that because magnets are weird and probably a little harder than you're ready for. All right, let's look at another example. So we have a mass that's attached to the ceiling at 2 points using ropes. What kind of forces do ropes apply? Both ropes make a 30-degree angle. So this right here, this is 30, and then this is 30. The brown lines are the ropes, and then this is just kind of like a reference, like invisible line, so that we can tell what we're talking about. Makes a 30-degree angle with the top of the mass. That's maybe a little misleading. With vertical. Okay, I drew it the way I want it. We want to draw a free body diagram of the situation. And when we say of the situation, we're talking about for the box right here, or the mass. Okay, so step 1, turn your mass into a point. Step 2, it's on a planet, so of course there's going to be weight or the force of gravity pulling straight down on this thing. Okay. Now we have 2 ropes here and they're pulling up. This one's pulling up and a little to the left, and this one's pulling up and a little to the right. What we're going to do is we're going to draw those separately because they're 2 separate objects applying a force. There's a lot of symmetry here, but there's still 2 distinct things, and we should have 2 distinct forces acting on our object. So for this one, I'm going to call this rope 1 and this one rope 2, just so that I can keep them straight in my own head. It's important to label things. So this one, for ropes. Ropes apply tension. Tension has an S. And tension, we said, has to be parallel to the rope or the string that's applying it. So that means our tension force for this rope 1 has to be 30 degrees from vertical. So maybe there's vertical. That's about 30 degrees. I'm going to call this capital T 1, capital T for tension. That's pretty normal. The second one is T2. So we're going to put that 30 degrees to this direction like that. Label it T2. You're going to notice that I drew these shorter than this. That's because for vectors, there's a difference between that and that. The direction of the arrow indicates direction. The way we indicate magnitude or how strong the force is with the length of these vectors. So if I draw it shorter, that means it's not pulling as hard. The reason I made these smaller is because this thing is just floating there, right? It's stuck, it's suspended by these ropes. So weight's pulling down. Weight needs to be canceled out by something so that it's just sitting there. So the up bit from these two together are canceling out the weight down. If they were the same size, I'd have more up than I do down, and then that wouldn't really make sense for this situation. Okay, cool. So there we go. There's a nice free body diagram. It's okay to draw dashed lines. You probably shouldn't put a plus sign in the middle of it, but notice this tension is a force, tension is a force, weight is a force. There's nothing but forces on this free body diagram. Okay, we got 2 more. So it says you are moving and you need to get your couch into the truck so you can so you slide it across the floor by pushing on one end. Draw a free body diagram of the couch while it's sliding. Okay. So we are looking at just this couch, so we're going to turn it into a point. Let's see. It's on Earth, so of course there's weight. That's kind of like a freebie gimme. The only time you won't have weight is when you're in space. And then even then, there's probably a force of gravity. Sorry, I was parched. I need a little sip of water. All right. Let's talk about what's going on with this couch. First of all, the couch is touching the ground, and it's not falling through the ground, right? So there's probably a normal force or a contact force between the couch and the ground that's supporting it to keep it from falling because of the force of gravity. So let's go ahead and put that on here. We're going to put an arrow up. We're going to label that N, lowercase n, for normal force. This is the force of the ground pushing up on the couch because it's solid. Okay. This push up from the ground is canceling the pull down from the earth. So I'm going to put little equal markers on there. Okay. Now here's you. You are pushing on the couch and you're pushing that direction. So we would put this arrow like that. It should start there, even though I'm pushing on the left of the couch. We don't want the arrow pointing into the point. We want the tail on the point and telling us which direction the force is going. How would we label this? So you're pushing. Technically, your hands are solid and the couch is solid, so you could label it a normal force or a contact force because of solid things pushing on each other. But usually when you have someone or something like a dog pushing or pulling, and it's not like a hard surface, there's not really a good reason for it. But usually we'll call this just an applied force. So I would just put capital F, and then maybe this person's name is Barton. So I would put FB for the force of Barton. You could also put FA for force applied. Or you could label this normal force 1 and this normal force 2. But some people don't really like that label. So it's whatever makes sense to you, really. All right. Now, why is it so hard for you to push couches? Like, why does this guy or girl, well, if it's Barton, it's probably me. Why am I struggling so hard to push a couch? Why are couches difficult to slide on floors? Oh, slide on floors. That means the couch is rubbing on this floor. The couch is trying to go that way. So a rubbing force would be friction, and friction always pushes opposite the direction the thing is trying to slide. So the couch is trying to slide to the right, so friction is going to push back and oppose me applying a force. We don't know a whole bunch about physics yet or how me pushing compares to friction, so we'll just draw it to the left without any real thought about length, how it compares to this. We're not going to mark them equal. We're not sure. There is a symbol we always use for friction, and it's lowercase f. We're going to have a whole lesson just on friction later, but for right now, you get the idea. All right. Any other forces? One way that you can check if you have all your forces is draw a circle around your object and ask how many things are touching it. I'm touching, so I have my applied force right there. Got that one. The floor is touching. Okay, well, that's the normal force. Got that one right there. It's sliding, so we got friction. And then the only force that can apply without touching is weight, and we've got that. So it looks like there's no strings attached, there's no springs, there's no rocket boosters. So this is our complete free body diagram. Last example. A mass is sliding down a ramp that's been polished so it's very smooth. Draw a free body diagram for the mass. So let's look at this. We have this mass. We're going to condense it down to a point. Okay. Weight is always towards the center of the earth. If this ramp is flat on the ground, the center of the earth is that direction from the mass. So we're going to draw our weight straight down. Okay. Now we need to be very careful with the normal force. The normal force, normal is a synonym for perpendicular. So what it's perpendicular to is the solid surface the object is on. So it's got to go that way. It's not straight up opposing weight anymore. It's perpendicular to the surface you're on. So it should be that direction. And we'll label it normal force. Okay. Should we put friction on here? Let's read the problem and explain why we wouldn't. A mass is sliding down the ramp that's been polished very smooth. Friction is because of rough surfaces. If you took a magnifying glass, what do magnifying glasses look like? Something like that. And then you looked here, and this is like one of those biology pictures where it like zooms way in, right? What this would look like zoomed in times 1,000 is the surface of this block would look something like this. And then the surface of most things will look like that. And when you try and slide these two things across, they get caught on each other because of the roughness of their surfaces. That's what friction is. It's two rough things snagging on each other and then kind of wearing each other down and whatnot. If we polish one of them so it's very smooth, then there's nothing for the other thing to get caught on, and then there's no friction. So because it says very smooth, that's like a physics like signal for you to say no friction. Okay. And then there's your notes. That's how you do free body diagrams. We could check if there's anything missing off here. Let's see. We've got weight, the only non-contact force. Let's look at this. The only thing touching this block is that solid surface, and we have the solid surface force. So this is our free body diagram. Okay, so I'm going to have some homework for you where you're going to either be drawing free body diagrams or maybe matching free body diagrams to pictures that I've drawn, things like that. If you have questions or you're unsure about some things, let me know. Go ask. Otherwise, don't forget to like and subscribe. Have a great day, you guys.